when I talk about why we care about limits, I'm going to be doing some referring back to our experiment with the bottle rockets. You guys all remember that? I know it was like 10 days ago, so it's probably left your memory by now. The bottle rockets. Do you remember it?
Oh, the water law thing.
Yes.
The water law.
Yes. Water, Newton's third law of motion. For every action, there's an equal and opposite reaction. Yes? You guys are learning about that in physics? Maybe? Okay. Anyway, so here's why we care about limits. So I'm going to give you the exact definition of a limit, which I hadn't given you yet. But then I'm also going to show you how it's used in practice, and then we're going to talk a little bit about your assignment today. So if you have a situation where you're looking for the limit as h approaches 0, so this part is what we've been covering now, and the next part's going to look really familiar from last chapter. And the limit I'm looking for is f of x plus h minus f of x divided by h. So you guys remember this from last chapter? Yeah. Okay, so if we look for the limit of this as h approaches 0, it ends up being something really special. Focus that a little bit. This ends up being the slope of the line tangent. Slope of the line tangent to f of x at x. Tangent to f of x at x. Okay, so I'll let you guys write that down before I explain why that's important and why you care about that, or why anybody would care about it. So taking two pieces, one piece from last chapter, one piece from this chapter, and I'm jamming them together. And by doing that, I'm able to find the slope of the line tangent to a function at any given point x. And why that's important is if we take a look at the bottle rocket stuff we were doing a week and change ago, if we wanted to find the instantaneous velocity of our rocket at any one point, like so it shoots up, comes back down. If we wanted to find the exact velocity it had at any one given number of seconds, we can use the slope of the line tangent to find that. That's what this is used for. This is one example of what it's used for. It's used for literally hundreds of things throughout a bunch of different careers. But for our example, we're going to be looking at astrophysics today. Or not even necessarily astrophysics. It could be like projectiles too. If you want to find the instantaneous velocity of an object, so the velocity at one specific instant, you need to use the slope of the line tangent. Now when I had you guys do the assignment on, not last Friday, but the Friday before, I had you guys use a secant line. Remember I had you find the how far it had traveled in like 1/10 of a second and then divide by 1/10 of a second. So, you know, place 2 minus place 1 divided by time it took to get there. So the definition of velocity, right? That's actually using what's called a secant line. However, using calculus, you can get more accurate by using the tangent line instead of the secant line, because the secant line is an approximation of what the tangent line really is. You guys remember me telling you that last week? Okay, one person nodding their head, so I'm not speaking Martian then. So there's this formula I gave you guys when we did the bottle rocket, and that is height at time t is equal to negative 1/2 gt squared plus v sub naught t plus h sub naught. And I actually made this formula a little bit easier for you guys a week and change ago, because I'm a nice dude. I don't think I included the g, and for all intents and purposes we left off the initial height. I know, because I know what gravity is on Earth in feet per second. Does anybody remember what, raise your hand if you can, remember what gravity is on Earth in feet per second? The acceleration due to gravity? That's meters. 9.8 meters per second squared.
That's something like 30
27.
No.
28.
No.
30.
Okay, so I'm dealing with things in feet per second here because I think it's easier for you guys to understand feet per second. But yes, acceleration due to gravity is 9.8 meters per second, or per second squared. But acceleration due to gravity in feet is 32 feet per second. So I'm going to just substitute in that 32 here for gravity. And then I'm going to leave this as t squared. I'm going to say that in this case we had an initial velocity. And looking at your initial velocities from last week, saying 50 feet per second wouldn't be, that's not too crazy. And let's say that we had an initial height height of 1.5 feet. So we're doing everything in feet and seconds here. Because I think it's easier for you guys to understand feet and seconds than it is to understand meters, because not a whole lot of people have a really good concept of how big a meter is, at least in America. I'm sure Gen has an excellent concept of how big a meter is. So if the initial velocity is 50 feet per second, this would be 50 t. And if the initial height is 1.5, this would be plus 1.5. And this is the formula for the height at time t. Now, for the moment, you just have to take it on faith. Well, I guess you don't. So the way that we found the velocity at the impact, at the second it impacted last week, is we used, we found out how long it took to impact. We found how high it was, like 1/10 of a second before the impact, and then we divided by 1/10 of a second. So we were using this equation here, and we used the secant line of this equation to approximate the impact velocity. I'm saying a lot of big words here. Are we okay? 2 people are okay with the huge words I'm throwing out. Okay, so we use the secant of the line that goes through 2 points to find the approximate instantaneous velocity. But if we could find the tangent, then we could find the actual instantaneous velocity, and that's where this comes in. So I'm going to take that formula for the rocket from last week, and I'm going to plug it into this up here. No, I know, I'm excited too. So negative 16t squared, I'm just going to make this a tiny bit easier, plus 50t plus 1.5. And I'm going to plug it into here. This is going to be my f of x, and in this case it's h of t. So I'm looking for the limit as h approaches 0 of, oh my gosh, all this good stuff. So we're going to do negative 16 times x plus h plus 50 times x plus h plus 1.5, and that counts as f of x plus h. And then from this we're going to subtract f of x, which is negative 16x squared plus 50x plus 1.5, all divided by h. So once we evaluate this, we're going to be able to have a nice, neat formula that will allow us to find the instantaneous velocity of the rocket at any time we want to. So we could find the instantaneous velocity 1/10 of a second after it launched. 2 seconds after it launched, 3 seconds, like whatever we want to. We can find the instantaneous velocity at any point once we evaluate this, okay? So let's do that. Oh yeah, and this is x plus h quantity squared. I forgot about that. So let's do that. Let's evaluate this. So the first part, this is what we were doing last chapter. So this shouldn't be too traumatic, but I could be wrong. It's a Monday. So, oh, you're right, it's Tuesday. Yes. So I'm going to first find out what x plus h quantity squared is. So that's x squared plus 2xh plus h squared. And then I can just distribute the 50 here. So plus 50x plus 50h plus 1.5. And then I can distribute this negative to everything inside. So this becomes plus 16x squared minus 50x minus 1.5. And this is all over h. And believe it or not, it only gets kinder from here. So my like terms here, plus 50x cancels with minus 50x, plus 1.5 cancels with minus 1.5, and those are my like terms so far. So I can already knock quite a few things out of the numerator. Now if I distribute this negative 16 to everything inside, I get negative 16x squared. I know, I'm excited too. Minus 32xh plus, or sorry, not plus, minus 16h squared. And then I have plus 50h, and then I have plus 16x squared, but that's going to cancel in a second. And then this is all over h. It only gets kinder from here. So my negative 16x squared and my positive 16x squared, those cancel. And yeah, cool. So once I divide everything by x, I'm going to be left with negative 32, or by h, negative 32x minus 16h plus 50. And I'm looking for the limit of this as h approaches 0. So now the limit comes back into play. H approaches 0. So for h, yeah. So if I plug in 0 for h, what am I left with? Well, not just the 50. So I'm left with plus 50, but I'm also left with, this part goes away, negative 32x. And x in this case would be a time that we would put in. So let's say we wanted to find the instantaneous velocity of that rocket 1 second after it launched. So, right, it would be negative 32 plus 50, which is 18 feet per second. If I wanted to find the instantaneous velocity 2 seconds after it launched, that would be negative 14 feet per second. 3 seconds after it launched, that would be whatever negative 96 plus 50 is, negative 44 feet per second. And with velocity, or did I do that right? Negative 46. So velocity, that negative means it's coming down. And that's the difference between velocity and speed, is velocity has a direction to it, whereas speed is just a unit with a magnitude, right? Kind of, sort of. So this here, you guys are going to hate me next chapter for having you do this the long way, this chapter. But this here, next chapter, I'm going to show you an easier way to do, but this is how we would find the instantaneous velocity of that rocket at any time t. Kind of, sort of? Okay, let's take a look at your assignment. Yes. 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 In fact, if you're ever curious about our schedule for the week, you need only direct your attention to the rear of the room where it says calculate.
Oh. No way.
I got a schedule for the week. Oh, because technically it doesn't matter. They use a 30 grade. I know that if you got that, but it's the same as I understand. So if you want to do it that way, feel free. Okay. So what I'm assigning for you guys tonight is 11 through 18, and then 19 is extra credit. Let's go through some of these together. No, 19 is extra credit.
Yeah, it must be hard.
Yeah.
Why don't you pass it? Yep, it's hard. There's 8. Because of 8 Bolton.
Yep. So I'm assigning 11 through 18, and then 19 is extra credit. Number 11 shouldn't be too hard. Number 11 is an extension of what we were doing last Thursday. But let's take a look at problem number 12. So problems 12 through 15 require a calculator. So grab your good old calculator. And the first thing it asks you to do is to find the limit as h approaches 0 of arctangent 0 plus h minus arctangent 0 divided by h. So wherever we see a variable here, we're going to put in x variable. Make sure that you're putting parentheses around your entire numerator, and I'm sure that you've forgotten what arctangent is.
Yep.
Okay. Arctangent is second tangent. It's tangent to the negative 1 power. Okay? So if you're entering that into your calculator, turn on the light so you can see it maybe a little bit better. So arctangent is tangent to the negative 1 power. So I'm going to put parentheses around my numerator, and then inside these parentheses I'm going to do second tangent, and then in parentheses 0 plus x variable. I'm going to close those parentheses, minus second tangent of x, and then I'm going to close parentheses for my entire numerator here. So my whole numerator is encapsulated in parentheses. Whoa. Sorry, what?
Alright.
I didn't hear what you asked. Minus, okay, arctangent of x, which is second tangent x, and then divided by x. It's going to be this weird little, like, lumpy thing. Yeah, so you can use, I think it's easiest to use the trace function on your calculator, or you can use the table function if you like. Okay, then use the table. Zero is going to be undefined.
Well, what is the answer?
We're getting there. I know. It's probably the window. Or it's either the window or the mode. Let's change ourselves to degrees, maybe? No, we want to be in radians. It should be there, but it should be like, we should see just a little teeny tiny bump.
All over H, right?
Yep. All over, well, X in this case, but yeah. What happens if I do trace? Okay, there we go. No, it's there. It's just teeny tiny. Yeah. So if I hit my trace button,
Just says Y is 0. Wait, did we just do that wrong?
did I do it wrong?
Isn't it arctangent 0 for the second one? So arctangent 0.
Yeah, I did do it wrong. Thank you. So Cash pointed out I made a mistake. Thank you, Cash. So it's arctangent 0 plus x minus arctangent of 0, and I did arctangent of x. Mr. Taft. Thank you. How do you do what? Okay. Faith, I don't always know if you're asking me a question or if you're just speaking your frustrations out loud. Okay. So if I go from here, you can either use your table or your trace. If I use trace, I can see that on one side at negative 1.5 for x, y is 0.99. On the other side at 1.5 for x, y is positive 0.99. So approximately, what value is it approaching? 0? The y value, yeah. What is the y value approaching, Michael? 0.99 on this side, 0.99 on this side. So add the two together and divide by 2. No. No, not the x value. The y value. 0.99. Positive 0.99. Right? You could even make the leap and say it's approaching 1, which is what it actually is. But if you put 0.99, I wouldn't mark that wrong.
Alright.
Okay, now B and C on number 12 are very similar. So I'm not going to go over those with you guys, but I will go over them with you individually if you need me to.
So we just need to tell you what the limit is approaching?
Yeah, and then, so it asks for a geometric interpretation. I don't need you to do that. I just need the number that it's approaching using your calculator. Now number 13, let's take a look at 13 together here. So first of all, it says, what is the limit as h approaches 0 of cosine h minus 1 over h represent? And then it tells you to recognize that this is equal to cosine 0 plus h minus cosine 0 divided by h. So this form right here from your notes means that it is similar to this up here, right? For number 13. So that means that this is the slope of the line tangent at x is equal to 0. So that's the answer to part A, to 13a. It's the slope of the line tangent at x equals 0. And then 13b, you're going to use your calculator to determine that. So the slope of the line tangent at x equals 0. And then if you want to do part B, which why wouldn't you? We're going to do parentheses around the whole numerator, cosine x minus 1, close parentheses, divided by x. And then I'm going to use my trace function, but you can use your table to evaluate it close to x equals 0. So I got that little jobby that shows up.
Wait, did you put 1 in cosine?
It's cosine h. So like when you're using the TID6, if you don't use parentheses, it only does the next thing as that function. So I don't need to put, if I'm just doing x, I don't need to put parentheses around the x. I don't know if you need to on the 30xs. So if I trace, it's approaching, so on this side it's 0.07, on this side it's negative 0.07. Now what do they average to, Mike? There we go. So that would be your answer to 13b. 14 and 15 are eerily similar, except 15 you don't have to say it's the slope of the line tangent at x equals blah. For 16, for A and B, I would suggest you just choose some random values for h to answer those. And then for the graph, you need to know where the absolute value function is on your calculator. If you need to know that, I can show you.
Like under more or something?
So on this one, so if we go to graph y of x, stop that. I know. It's super needy. It needs me to move the mouse often. We need to go to second math, and then under here it's under number and absolute value. This is for the TI-86. For the TI-30XS, there's no absolute value function. So you got to use like Desmos or something.
Well, when I use Desmos and I put, I don't know, it didn't work.
Okay, I can second math, and then F1 for num, and then F5 for absolute value, or anti-life brake system. And then we end up with this. So this is for number 15, so, or 15C anyway. So if we look at this, the limit as h approaches 0 from the left, so the left-handed limit would be about what? -1. Yes, it would be -1 from the left. What would the right-handed limit of the function be? 1. And then what's the general limit? Does not exist, because if the left-hand and right-hand limits are not the same, the general limit does not exist.
What number is this?
75. I know, and you're not paying attention. Okay, it's 15. But not part A or B. Part A or B, I said that you just need to choose some random numbers. 16. Oh, okay, 16. I misspoke. 17 and 18 are very similar too. So connected and smooth. So like you just have to put a letter next to each of these, or just on your paper next to each of these to say which one of these fits it. So connected and smooth. So like -1. Connected and smooth means there's no jump, and it goes nicely. Connected with a corner means it has a corner, makes a turn. Not connected because of a simple hole is like question number 1, or not question number 1, is like at x equals 1. And not connected because of a vertical jump is like at 2. So like right away it's A, B, C, D. Excuse me.
Right where it's at.
Yeah. So like the way I did it on the answer key is I just wrote A, B, C, D. And then this one has a hole, which is B. Or no, not B, C. This one has a corner, which is B. And this one is connected and smooth, which is A. Yeah. And then 18 is shockingly similar to that. And then 19 is a proof where you're given the statements and you have to come up with the reasons, but that's extra credit. Okay? Some of the reasons, like if you can even come up with one reason, I'll still give you extra credit. Because like some of them aren't that hard to come up with. Like part A, it's not that hard to figure out the reason for that. But yeah. Okay, come around and help anybody who needs it.